Grounding in a house electrical system involves several key components. Firstly, there is the ground rod. This is a copper or galvanized steel rod that's driven into the earth, usually 8 to 10 feet deep. Its primary function is to act as a conductor, providing a path for electricity to safely dissipate into the ground. Secondly, there is the grounding electrode system, often abbreviated as GES. The grounding electrode system consists of the ground rod and any other conductive paths connecting to the earth. These additional paths can include things like metal water pipes, the metal frame of the building itself, or concrete encased electrodes, often called UFA grounds. Thirdly, there is the ground bar in the electrical panel. This is typically a metal bar located within the electrical panel, often at the bottom. Its purpose is to serve as a central collection point for all the grounding conductors originating from various circuits and equipment within the electrical system. Now let's look at the grounding connections. There are a couple of common options for how these components are connected. In option 1, the ground conductor originating from the ground bar in the electrical panel connects directly to the ground rod. In this configuration, a separate ground conductor then runs from the ground rod to the meter base. In option 2, the ground conductor from the ground bar in the panel connects to the meter base. In this setup, a separate ground conductor runs from the ground rod to the meter base. It is important to note that in both options, the ground rod and the electrical panel must be connected to the grounding electrode system. The meter base is also typically connected to the grounding electrode system. Having multiple grounding paths provides redundancy, meaning that if one path fails, there's another path available. This redundancy significantly improves overall safety. To help visualize this, let's look at a schematic representation. For option 1, we have the ground rod connected to the ground bar, which is connected to the meter base. For option 2, we have the ground rod connected to the ground bar. The ground bar is connected to the meter base, and the ground rod is also directly connected to the meter base. Always consult with a qualified electrician for proper grounding installation and maintenance. Improper grounding can be dangerous and violate electrical codes. Grounding ensures that in the event of a fault, such as a short circuit, the electrical current has a safe path back to the source, tripping a circuit breaker or fuse and preventing electrical shock or fire. The National Electrical Code, or NEC, provides specific guidelines for grounding requirements. These requirements vary depending on factors such as the size of the service, the type of building, and the local soil conditions. Ground rods are typically made of copper or copper-clad steel to resist corrosion and provide a good electrical connection to the earth. The depth of the ground rod is important to ensure it reaches a sufficiently conductive layer of soil. In areas with dry or rocky soil, multiple ground rods may be required. The connection between the ground conductor and the ground rod must be made with a listed connector suitable for direct burial. These connectors are designed to resist corrosion and maintain a reliable electrical connection. The ground conductor itself is typically a bare copper wire or a green insulated wire. The size of the ground conductor is determined by the size of the service entrance conductors, as specified in the NEC. The grounding electrode system should be inspected periodically to ensure it is in good condition. This includes checking the ground rod for corrosion, the connections for tightness, and the ground conductor for damage. If any issues are found, they should be addressed immediately by a qualified electrician. In addition to the ground rod, other grounding electrodes may be present. Metal water pipes can serve as grounding electrodes, but only if they are in direct contact with the earth for at least 10 feet. The metal frame of a building can also serve as a grounding electrode if it is effectively grounded. Concrete encased electrodes, also known as UFA grounds, are installed during the construction of a building. They consist of a length of rebar encased in concrete that is in direct contact with the earth. The grounding electrode system is connected to the neutral conductor at the service entrance. This connection is called the main bonding jumper. The main bonding jumper ensures that the neutral conductor and the grounding system are at the same potential, which helps to prevent voltage differences that could cause electrical shock. The equipment grounding conductors in each circuit also connect to the ground bar in the electrical panel. These conductors provide a path for fault current to flow back to the source, tripping a circuit breaker or fuse. Equipment grounding conductors are typically green insulated wires or bare copper wires. They are connected to the metal enclosures of electrical equipment, such as appliances, lighting fixtures, and receptacles. It is important to distinguish between grounding and bonding. Grounding refers to connecting the electrical system to the earth. Bonding refers to connecting different metal parts of the electrical system together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. Improper grounding or bonding can create dangerous conditions that could lead to electrical shock or fire. Always consult with a qualified electrician for any electrical work. Electrical work can be dangerous if not performed properly. A qualified electrician has the knowledge, skills, and experience to ensure that electrical work is done safely and in accordance with the NEC and local codes. When a fault occurs, such as a wire coming loose and contacting a metal enclosure, the grounding system provides a low impedance path for the fault current to flow back to the source. This high current flow causes the circuit breaker or fuse to trip, interrupting the circuit and preventing the metal enclosure from becoming energized. Without a proper grounding system, the metal enclosure could become energized, creating a shock hazard. The grounding system also helps to protect against voltage surges caused by lightning or other disturbances. Voltage surges can damage sensitive electronic equipment. The grounding system provides a path for the surge current to flow to ground, protecting the equipment from damage. The NEC requires that all electrical equipment be properly grounded. This includes appliances, lighting fixtures, receptacles, and electrical panels. The NEC also specifies the size and type of grounding conductors that must be used. The grounding system must be inspected regularly to ensure that it is in good condition. This includes checking the ground rod for corrosion, the connections for tightness, and the ground conductors for damage. Any problems with the grounding system should be corrected immediately by a qualified electrician. The cost of installing and maintaining a proper grounding system is relatively small compared to the potential cost of an electrical shock or fire. A proper grounding system is an essential part of a safe electrical system. It protects people from electrical shock and helps to prevent electrical fires. In summary, the grounding path in a house electrical system involves connecting the ground bar in the electrical panel to a ground rod and the meter base. This creates a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock or fire. The grounding system must be installed and maintained in accordance with the NEC and local codes. Always consult with a qualified electrician for any electrical work. Remember, electrical safety is paramount. Grounding is more than just sticking a rod in the ground. It's a carefully engineered system designed to protect lives and property. The NEC undergoes revisions every 3 years to keep up with new technologies and address emerging safety concerns. It's important for electricians to stay up to date on the latest code requirements. Some local jurisdictions may have additional electrical codes that are stricter than the NEC. It's important to be aware of these local codes and comply with them. The grounding system should be designed to minimize the impedance or resistance to ground. This ensures that fault current can flow quickly and easily back to the source, tripping a circuit breaker or fuse. The impedance of the grounding system can be affected by factors such as the length and size of the grounding conductors, the type of soil, and the quality of the connections. In some cases, it may be necessary to install multiple ground rods or use a chemical ground rod to achieve the required impedance. A chemical ground rod is a hollow rod filled with chemicals that improve the conductivity of the soil. The chemicals slowly leach out into the surrounding soil, creating a more conductive path to ground. Chemical ground rods are typically used in areas with poor soil conditions, such as rocky or sandy soil. The connection between the ground conductor and the ground rod should be made with a crimp connector or a compression connector. These connectors provide a secure and reliable electrical connection. Screw-type connectors are not recommended for grounding connections because they can loosen over time. The ground conductor should be protected from physical damage. This can be done by running the conductor through conduit or by burying it underground. The ground conductor should also be protected from corrosion. This can be done by using a copper or copper-clad steel conductor and by coating the connections with a corrosion inhibitor. The grounding system should be tested periodically to ensure that it is functioning properly. This can be done with a ground resistance meter. A ground resistance meter measures the resistance between the grounding system and the earth. The resistance should be low enough to allow fault current to flow quickly and easily back to the source. If the resistance is too high, the grounding system should be inspected and repaired. In addition to the grounding electrode system, there is also the equipment grounding system. The equipment grounding system is a network of conductors that connects the metal enclosures of electrical equipment to the grounding electrode system. The purpose of the equipment grounding system is to provide a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse. The equipment grounding system includes equipment grounding conductors, bonding jumpers, and metal raceways. Equipment grounding conductors are typically green insulated wires or bare copper wires. They are run with the circuit conductors and connected to the metal enclosures of electrical equipment. Bonding jumpers are used to connect different metal parts of the electrical system together, such as metal water pipes and metal gas pipes. Metal raceways, such as conduit and cable trays, can also serve as equipment grounding conductors. The equipment grounding system must be installed in accordance with the NEC. The NEC specifies the size and type of equipment grounding conductors that must be used. The NEC also specifies how the equipment grounding system must be connected to the grounding electrode system. The equipment grounding system must be inspected regularly to ensure that it is in good condition. This includes checking the equipment grounding conductors for damage, the bonding jumpers for tightness, and the metal raceways for corrosion. Any problems with the equipment grounding system should be corrected immediately by a qualified electrician. The grounding and bonding of electrical systems are complex topics. It is important to have a good understanding of the NEC and local codes before attempting to install or repair electrical systems. Always consult with a qualified electrician for any electrical work. The electrical safety is paramount. In some situations, a supplemental grounding electrode may be required. This is typically the case when the soil resistivity is high or when the grounding electrode system is not providing adequate protection. A supplemental grounding electrode can be a ground rod, a ground plate, or a chemical ground rod. The supplemental grounding electrode should be installed as close as possible to the equipment that it is intended to protect. The supplemental grounding electrode should be connected to the equipment grounding system with a bonding jumper. The size of the bonding jumper should be determined by the size of the circuit conductors. The grounding system should be designed to protect against both overcurrent and overvoltage conditions. Overcurrent conditions occur when the current in a circuit exceeds the rated capacity of the circuit conductors. Overvoltage conditions occur when the voltage in a circuit exceeds the rated voltage of the equipment. Overcurrent protection is typically provided by circuit breakers or fuses. Overvoltage protection is typically provided by surge protective devices. Surge protective devices, or SPDs, are designed to protect against voltage surges caused by lightning or other disturbances. SPD are typically installed at the service entrance and at branch panel boards. SPD should be selected based on the voltage and current rating of the electrical system. SPD should be installed in accordance with the manufacturer's instructions. The grounding system should be designed to minimize the risk of electrical shock. Electrical shock can occur when a person comes into contact with an energized conductor and ground. The severity of the shock depends on the voltage, the current, and the duration of the contact. The grounding system helps to reduce the risk of electrical shock by providing a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse. The grounding system also helps to reduce the voltage on metal enclosures of electrical equipment. The NEC requires that all electrical equipment be properly grounded. This includes appliances, lighting fixtures, receptacles, and electrical panels. The NEC also specifies the size and type of grounding conductors that must be used. The grounding system must be inspected regularly to ensure that it is in good condition. This includes checking the ground rod for corrosion, the connections for tightness, and the ground conductors for damage. Any problems with the grounding system should be corrected immediately by a qualified electrician. The grounding system is an essential part of a safe electrical system. It protects people from electrical shock and helps to prevent electrical fires. The proper installation and maintenance of the grounding system is critical for electrical safety. Always consult with a qualified electrician for any electrical work.